Hello, dear students of third year secondary. This is physics session. My name is Ahmad and I teach physics. Today, inshallah, we continue talking about chapter 7. Last time we talked about the crystals and how doping crystals can increase the conductivity of electric current inside them. And we said that we have two types of semiconductors. We have the N type and the P type. And we have said that the semiconductors doped with impurities of pentavalent elements in which the concentration of the free electrons bigger than the concentration of holes, we will have the N type. And in case we talk about the P-type semiconductors, they are doped with impurities of trivalent elements and in which the concentration of holes bigger than the concentration of free electrons. Now, today we would continue talking about the NP junction, but before this, we need to compare between the N-type and P-type concerning a very important law, which is called the law of mass action. And the law of mass action governs what's the concentration of charge carriers. I mean, charge carriers can either be electrons or they can be holes. So addition of N-type impurities decreases the number of holes below a level, and similarly the addition of P-type impurities decreases the number of electrons below a certain level. And it has been experimentally found that under thermal equilibrium for any semiconductors, the product of the number of holes and the number of electrons is constant, and the independent, it's independent of the amount of doping, and this relationship is called the law of mass action. To represent this in a form of formula, we have N times P. N here stands for the concentration of free electrons. P stands for the concentration of positive holes. And the product of their multiplication will give me N sub I squared. N sub I squared is the concentration of any charge carrier, and I here stands for intrinsic. Now, if we like to explain what does it mean, it means that if I multiply the concentration of negatively carriers, or negative charge carriers, electrons, free electrons, and we multiply this by the concentration of positive holes inside the Pn junction, I will have constant, and this constant is N sub I squared, and N here is the electron concentration and P the hole concentration, and N sub I is intrinsic concentration. Now, what we mean by N sub I is the intrinsic concentration, which means that the concentration of charge carriers. And we know that we have two types of charge carriers, free electrons or positive holes. So N sub I stands for intrinsic. N sub I means concentration of charge carriers, or which mainly means electrons or holes, because charge can be carried by either one of them. Now, from the law of mass action, the concentration of electrons is inversely proportional to the concentration of holes. And why is that? Because going back to the law, we have two things multiplied by each other equals constant. N sub I squared equals constant. When I have two variables and their multiplication or product is constant, it means that they are inversely proportional to each other. This is from math. Now, therefore, because they are inversely proportional, I can draw the relationship between P, concentration of positive holes, and the reciprocal of N, the reciprocal of the concentration of free electrons, and I will have a straight line like this. Pay attention, it's reciprocal of concentration of free electrons, not the concentration itself. It's the reciprocal. Otherwise, the shape of the curve will change. Now, building on what we have studied so far, the N-type semiconductors, I have the concentration of holes much bigger than the concentration of free electrons. And this is because it is, what's the meaning of P-type semiconductors? It means that from the definition, p-type means it has more positive than negative. So the concentration of positive holes, p, much bigger than the concentration of free electrons. So we can put it in a different way. Electrons are minority carriers and holes are majority carriers. What do we mean by minority carriers? They carry the, the charge, but they are found in very few amounts, which we call this minor carriers, because the number of them is low or their concentration is limited. Now, on the other side, the holes are called majority carriers because most of the currents or most of the charges, they are found in the form of positive holes, and that's why we call it majority carriers. This is talking about the p-type semiconductors. Now, on the other side, if we compare this with the n-type semiconductors, we have the opposite, exact opposite. N much bigger than P. What does it mean? The concentration of free electrons much bigger than the concentration of positive holes. And because of this, I call the holes minority carriers and electrons majority carriers. What does it mean? I have more electrons than holes. So what is the responsibility of free electrons? They carry the charge. That's why they are called majority carriers. Now, I want to remind you of the two types of semiconductors that we have taken last time. We have electron acceptors and we have electron donors. And if you remember, I can dope or add impurities to a pure crystal of silicon by adding aluminum or boron. Now, if I add aluminum or boron, because either of them is trivalent, it has 3 electrons that can be shared, form bonds. And if you have a pure crystal doped with trivalent elements such as aluminum or boron, I will have p-type crystal. Now, what will happen if I dope the pure crystal with something like pentavalent, such as phosphorus or antimony? I will have extra electrons, which means that I will have n-type crystal. So this is what we have covered last time. Electron acceptors found in p-type, electron donors, they are in n-type, and that's because of the doping or because of the impurities that I add to the pure crystal. Now, and to summarize this, I have two symbols here, Na minus. What does it mean? N stands for concentration, A stands for electron acceptors, and minus here stands for the charge, the overall charge on it. So N sub A minus is the concentration of electron acceptors. Now, electron acceptors found in p-type. Yes, p-type here, you have, in the p-type, you have the concentration of electron acceptors N sub A negative. Now, similarly, I can put the symbol of the concentration of electron donors. Electron donors means the impurity that will donate a free electron to the crystal. And that's because it donates an electron, so it will change to positive. Because it will release negative, so it will change to positive. And we have a sample for this, which is N sub D plus. N sub D plus here is what? Is the concentration of the electron donors. And because they donate electrons, they will have a positive charge. So what's found in p-type? I have electron acceptors. What's found in n-type? I have electron donors. And that's very important if you would like to discuss and explain the law of mass action, because I have here a comparison between the n-type and the p-type. In the n-type, the law of conservation of a charge tells me that the sum of negatively charged carriers or particles equal the number of positively charged. So this is from the law of conservation of a charge. So what is the negative part? The negative part represented by the concentration of electrons, which is n, small n, equals the sum of the positive. particles. Now, what are the positive? The holes, positive holes, plus N sub D plus. What's N sub D plus? It is the concentration of electron donors. Electron donors, they have positive charge. Holes, they have positive charge. So P plus N sub D plus, this term, the right-hand side, represents the positive part inside the N-type crystal, and N small represents the negative particles inside the N-type crystal. And we equate them. Similarly, concerning the P-type crystal, also the positive, the sum of the positive equal the sum of the negative from the law of conservation of a charge. Now, what is the positive part? The holes, P, concentration of holes, P, equals, what's the negative part? The negative part, I have electrons, and also I have electron acceptors. Now, what do we mean by electron acceptors again? They are the impurity atoms that I added to the pure crystal. And because they accept electrons, they will have extra negative charge. So here, P, the sum of the left-hand side, P equals the positive part, represented here by the concentration of holes, equals the sum of the negative part, which is the free electrons concentration, N small, plus N sub A minus, which is the concentration of the electron acceptors impurity. Okay, this is concerning the sum of positive and negative in both N and P type. Now, if you look here at what's happening in N type, I have the concentration of holes much less than the concentration of the electron donors. Now, electron donors N sub D plus, they are found in big number than the holes because the type itself of this crystal is N type. So from the definition of N type, I have few numbers of holes and much less than the concentration of impurities, which are the electron donors, N sub D plus. Now, similarly, if we compare this with the P-type crystal, we have the exact opposite. The concentration of free electrons much less than the concentration of the electron acceptors, impurities, which means that from the definition of P-type, I have very, very little free electrons because I have the opposite. The charge carriers, majority, they are actually the positive holes. So from here, compare this part with the above part, we can say that if something is very, very small in comparison with something else, I can neglect it and it will not affect the equation very much. So from here, N equals P plus N sub D plus. I can now consider this part, which is the concentration of holes in the N type. I can consider this part very, very small and I can neglect it. Now, if I neglect the P, the concentration of holes, I will have the concentration of free electrons equals N sub D plus. So this equation is the same like the above one. The only difference is I cancelled the P. And I cancelled this P just because this P, concentration of holes, much, much smaller than the concentration of electron donors. That's why. Similarly, I can do the same thing here talking about the P-type. So in the P-type means I have more holes than free electrons. So the number of free electrons in the P-type crystal is much, much smaller than the impurity, which is the concentration here N sub A negative, which is the concentration of electron acceptors. So in this case, when in the free electrons, the concentration of free electrons much, much smaller than the concentration of electron donors, electron acceptors. When I have this, I can also neglect the N in the equation, the small n in the equation, and I will have P equal n sub A negative, which is the electron acceptors. Now, I still have from the law of mass action that the product of n times P, n stands for the concentration of electrons, free electrons, and P stands for the concentration of positive holes. And if I multiply them by each other, they give me n sub I squared, which is constant. What's n sub I? The intrinsic concentration, which is the concentration of charge carriers. It can be electrons or holes. Now, by comparing this with the above part, I can now take this one, P equal divide n sub I squared divided by n sub d plus. N sub d plus is actually n, the concentration of free electrons. So what did I do? I replaced this n by n sub d plus in the law of mass action. Similarly, I can do this, the same thing in the p type. I can write here n equals n sub I squared divided by, I should write p, but I replaced p in the denominator by n sub A minus, which is the concentration of electron acceptors. So this is how to adopt the law of mass action in both types of crystals, the N type and the P type. We have many applications on that. When he gives you like a question, you can apply the same technique to solve it. Now let's talk about the Pn junction. The Pn junction is extremely important because it's the background needed to understand all kinds of electronics. And it is the start also to understand how to build up diodes and how to build up transistors. And because these two things, diodes and transistors, they are the keystones of electronics. So to understand the Pn junction and how it functions, we have some introduction to do. Now, we have first the shape of the Pn junction. If you look at that diagram, this diagram has two parts, and there is a part in between. So look at this part, the right-hand side. It's called the N-type crystal. So simply, the Pn junction is attaching N-type crystal with the P-type crystals, and then you can connect it to an external electric current or electric potential source. All right, so you have N-type crystal and P-type crystal, you attach them to each other, and then you connect it to a battery. So as you see here from the N-type, the charge carriers are free electrons. The negative charge here represents free electrons. Now, the left-hand side is the P-type crystal. Now, the P-type crystal contains positive holes. Positive holes, you can think about positive holes as places where like electrons left or electrons are no longer there. It's a vacancy of electrons. So you can think about holes as vacancy of electrons. All right. So I have here the P-type, the major charge carriers are holes, positive holes. The N-type crystal, the major charge carriers are free electrons. And if I put them together, I will have the Pn junction. Junction means connection between two things. So the Pn junction is the what we would like to talk about in this part. So in this case, we have first to investigate what's the meaning of Pn junction. To start with, if you look at the Pn junction here, what's going on? Here you have negative charges, and here you have positive charges, the positive holes. And because of this, I have two different kinds of charges. So when I have two different kinds of electric charges, I must have electric current. So think of the two types of crystals. Here you have negative and here you have positive. So in this case, as you see, the concentration of the free electrons on the right-hand side in p-type is much higher than the concentration of the positive holes in the p-type. So in this case, some of the charges will diffuse or pass between n-type and p-type. When they move in between, I have something called diffusion current. So the diffusion current results from moving charges, and this moving charges happens because of the difference in concentration between charges. Mainly in n-type, I have more free electrons, more negative charges, and that's why electrons will diffuse from the n-type crystal toward the p-type crystal, and this is what we call diffusion current. Similarly, I have in p-type crystal, I have more concentration of positive holes, so the positive holes will also diffuse from the p-type toward the n-type, and this kind of diffusion causing the diffusion current. Now, pay attention to something very important, because I have like carriers going between n-type and p-type, but what is the direction of diffusion current? The conventional way of expressing current is the movement of positive charges. So as you see here, what is the positive part? The holes. The holes are positive. So what's the direction of the positive charges from the p-type in the direction of the n-type? So in this case, we have diffusion of the positive holes from p-type toward the n-type. In this case, this is the direction of diffusion current. So to go back here and define what is the meaning of diffusion current simply is passing of some positive holes from the p region to the n region in the Pn junction. Similarly, passing of some negative electrons from the n region to the p region will also cause diffusion current. So which one of them I consider the diffusion current direction? In conventional way, the current is actually the diffusion of the positive charges to direction, takes the positive charge direction, which is passing of holes. Okay, so passing of some positive holes from the p region to the n region is the direction of diffusion current. Now, but if you look here, what's going on? Look at the diffusion. Like this is the negative charge, okay, and passing the negative charge represented by dashes means negative. So these electrons, they pass from the n to in the direction of p. Similarly, the positive from the p junction to the n junction. Now, do you think this kind of movement will carry on forever, or it will eventually stop? I think it will eventually stop, and that's a right guess, because as electric charges they move between the n-type crystal and the p-type crystal, there will be a time when I have electric field is built between the two junctions, and this electric field will result in something strange, that the carriers will stop moving between the two of them, the two regions. And when this happens, I have something called depletion region. The depletion region is a region between the n-type and p-type, where carriers of charge will no longer be able to pass between. And this region will prevent or will become like a barrier between the two of them. So the depletion region is at the contact of the two junctions, the P junction and the N junction. And what does it do? It does not contain charge carriers. And because it does not contain charge carriers, the diffusion will stop. But when this diffusion will stop? When this diffusion will stop? Good question. Look here at, this is the Pn junction, and I applied here the cathode and here the anode. Here I have the negative part and the positive part. Now holes and electrons, they keep moving until I have depletion region, which is the part in between. So diffusion and depletion region or depletion layer between them will prevent moving. Here I have the charges, it's the same thing. And because once the charge carriers they move between, I will have electric fields built between the N and P junction. And once I have a built up electric fields, I will have drift current. Now, what do I mean by drift current? The drift current is a current which results from the electric field built. And this electric field is called internal electric field. Why it's internal? Because it's not applied by an external source of electricity, such as a battery, but it is a field which is a result of building up different types of charges. And building up different types of charges, they result in the drift current. What is the drift current? The drift current is a result of the internal electric field between the N type and the P type, and it results from different types of electric charges of ions on both sides. Now, positive ions are in the N region and the negative ions are in the P region. And because of this, I have electric field. So let me tell you this again about the internal electric field. The internal electric field between the N type and the P type. And how did it come about? It came from or as a result of different types of electric charges of ions on both sides. And because I have one side positive and one side negative, I have the positive ions are in the N region. Why the positive became in the N region? Because electrons moved from this contact area to the other side. And because electrons migrated to the other side, this area now in contact between, it is now positive ions. Now, similarly about the P region, I have negative ions. And where did it come from? It's supposed to be positive. It became negative because electrons migrated from the N region toward the P region. That's why I have now negative ions in the P region. Now, when I have an electric field built now between the N and P types, electric current passes, and this electric current will be opposite to the direction of diffusion current. Previously, we said that diffusion current is the current represented by moving the positive holes, and the drift current is opposite in direction to the diffusion current. All right. Now, so I have two currents now. One current results from diffusion of charges, and another current results from the electric field, the internal electric field, and they are against each other in direction. Now, this cannot go on forever. There will be a time when the two currents will be equal to each other, and as a result, I will have a barrier. Currents will stop. So, in this, as you see here from this diagram, the P type, I have hole diffusion. Hole diffusion represents the current of diffusion or diffusion current. It goes from the P type toward the N type. Now, so the direction of holes from the P type to the N type, and that represents the diffusion current. If you look here down, you have an opposite current, which is called the electron current. The electron current moves the other way around. How about the drift? The drift is going from this place to that place. Holes will drift this direction from N type to P type, and electrons will drift from the P type to the N type. So, what is the direction of diffusion current? From left to right, from the P type to the N type. Now, go down. What is the direction of the drift current? The drift current from the right, N type, to the left, the P type. So can you see now they are opposite to each other? The whole diffusion represents the diffusion current, which is from the p-type to the n-type, from left to right. Now, if you go down to the diagram down, the drift current is actually the whole drift, which is from right to left, from the n-type to the p-type. All right? So don't be confused between the two currents, and this will not go on forever. It has to stop at one point when the two currents are the same. If the two currents are the same, something strange will happen. I will have a voltage barrier between the n-type and p-type. And when I have a voltage barrier, current will stop. What's the voltage barrier? The voltage barrier is simply, it is the least potential difference at the two sides of the Pn contact region, which is enough to prevent the diffusion of more holes and electrons to the low concentration region of them. Let me explain this part by part. So the voltage barrier is preventing the diffusion of any current, because when the voltage barrier is built, no currents can go, because I have now the two currents equal to each other. The diffusion currents equals the drift currents. They are equal in magnitude, they are opposite in direction. So when this happens, I will have voltage barrier. So the voltage barrier is the least potential difference. The least potential difference able to stop what? To stop any current. So it is the least potential difference. Where it is found, it's found at the two sides of the Pn contact region, so between the N and P type. Now, this potential difference is enough to prevent the diffusion of more holes and electrons to low concentration region of them, which means that the voltage barrier will stop diffusion current. Now, how can we connect the Pn junction? After understanding the Pn junction and what's happening and all these definitions, we have two types that we need to pay attention to, two types of connection for the Pn junction. If I connect the two crystals, the P crystal and the N crystal, I have two ways to connect them. Now, P and the N, they attach each other. So the only difference now is the external connection. The external means that how can I apply an external voltage, mainly from a battery. I have two ways: forward biased connection and reverse biased connection. Forward means in the same direction, and reverse means in the opposite direction. So if you look here here I have a Pn junction, and as you see, this is how it looks. Now, from N type, I connect it to the negative pole of a battery, and the P type crystal, I connect it to the positive pole of a battery. So in this case, the negative with the negative, the positive with the positive, what happens is electrons from the battery, from the negative pole of the battery, will repel the electrons in the N-type crystal, resulting in pushing electron toward the area of connection between the two crystals. Similarly, if you look at the left-hand side, the positive pole of the battery is connected to the P-type crystal. So in this case, the positive of the battery will also repel the positive holes in the P-type crystal, resulting in pushing the holes toward the connecting region between the P and the N. Now, this kind of connection actually helps the current to build up and overcome the resistance. So I simplify here what's happened. This is the N. I connect the N to the negative of the battery. Here I put the negative between brackets. And I connected the P, which represents the positive holes, to the plus or the positive pole of the battery. We call this forward biased connection. forward bias connection because the negative with the negative, the positive with the positive. Negative means the N-type crystal, where I have electrons connected to the negative pole of the battery. And the positive, which is the positive crystal, which contains positive holes, connected to the positive pole of the battery. So in this case, I call this, again, forward bias connection. And connecting the Pn junction in the forward bias connection has specific characteristics. But what happens if I reverse the polarity? Okay, as you see here, the charge will build. We go back to this diagram again later. But as you see here, what happens is in the forward biased, the current here is getting very high with little change in voltage, which means that this kind of connection is favored to get bigger current. We go back to this diagram, but now how about connecting in the Pn junction in a reverse biased connection, which is the exact opposite? I cannot change anything in between, like I have N-type and P-type. The only thing I can do is reversing the poles of the battery. So look here at the N-type has negative electrons. Now, these negative electrons, I will connect this N-type crystal to the positive pole of the battery. And I will connect the P-type, which contains the positive holes, to the negative pole of the battery. Now, the exact opposite. Now, in this case, look what will happen. The positive of the battery will attract the negative in the N-type, mainly the electrons. And because of this, electrons will shift away from the region in between the two types, the P and N, which will increase the depletion zone or the depletion region. Similarly, connecting the P-type that contains more positive holes with the negative pole of the battery will also result in a similar effect, which attraction between the positive holes in the P-type crystal with the negative pole of the battery. Now, when they are connected away, the depletion region or zone will also increase. So the reverse bias connection will increase the depletion zone or region because it pulls away the charge carriers away from the middle part between the two junctions. All right? So here, this is the current in the forward operating region. And if it is reversed, this is what will happen. So to summarize this kind of stuff, talking about the Pn junction and how they function inside, simply we can put it this way. In the P-type crystals, when they are connected to positive terminals of the battery, when they are connected to the positive terminal of the battery, the P-type crystal is connected to the positive terminal of the battery, and the N-type crystal is connected to the negative terminal of the battery. This is the forward. In the reverse biased, the P-type of crystal is connected to the negative terminal of the battery, and the N-type crystal is connected to the positive terminal of the battery. Now, what about the effect of external potential difference on the junction? External means applied by external source, such as a battery. Now, the direction of the external field of the battery is opposite to the direction of the internal field in the transition region, and therefore it weakens it. This happens in the forward biased connection. In the forward biased connection, I have the direction of external field, which is the results from the battery, opposite to the direction of the internal field. And therefore, it weakens it. They weaken each other. So the external weakens the internal. But in biased connection, the exact opposite happens. The direction of external field due to the battery is the same direction of the internal field in the transition region, and therefore it strengthens it. It makes it bigger, stronger. One important difference between also the two types of connection, the forward and biased, the voltage of the Pn junction. They are different, not the same. If I connect the Pn junction forward, the voltage of the Pn junction becomes less than the barrier voltage, which means that the current will increase. Now, if I connect it in the opposite way, which is the reverse biased connection, the voltage of the Pn junction will become greater than the barrier voltage, which is the exact opposite. One other part of comparison between the two of them is the thickness of the transition region. The transition region is the region between P and N. The thickness of transition region decreases, which means in the forward direction, the thickness decreases. And that's because the charges are repelled by the polarity of the battery. And when they are repelled, they come closer to the depletion region. And that's why the thickness of the transition region between the two types decreases in the forward. When I connected the Pn junction in the reverse biased direction, I will have the exact opposite. The thickness will increase. So thickness in the reverse connecting in the reverse bias, the thickness of the transition region increases, which means that holes and electrons, they attract with the poles of the battery. And because they attract to the poles of the battery, they go away from the transition region, and that's why this region becomes thick. How about the resistance of the junction? The junction itself, if we consider the resistance means the opposition to current. Now, in the forward direction, as you see here, in the forward direction, the current goes from this part to that part, which happens in the forward biased easy. Here positive with positive, negative with negative. This is forward. So the current here is the current is bigger, which means that the resistance is smaller. We know from chapter 1 that resistance and current, they are inversely proportional to each other, which means that if the current is bigger, the resistance is smaller. So in the forward biased connection, the resistance of the junction, or the ohmic resistance, is small. But in the reverse biased, I have the exact opposite. The resistance, the ohmic resistance, is large. Okay, it's large because the current is small. The last point is connected also to the current. In the forward, the current direction is high, has high intensity. In the reverse, has, of course, lower intensity, opposite to each other. But after comparison between the Pn, like if they are connected in forward biased connection or reverse biased connection, let's ask ourselves a question. What is the use of the Pn junction? Why we study it? Why it is important? Now, to start with, Pn junction by itself has many applications, okay? Other than just getting us prepared to understand the transistors and other things, but also by itself it has functions and it has uses. The Pn junction has many uses. Mainly two uses are important. We can use them as a switch. If you look here, the current can pass from this part, that part, in the forward direction. If the current tries to reverse its direction, it will not be able to do this. Now, because of this, the Pn junction can, when it's connected in this forward bias, can allow the current to have one direction and not the other. So it can act like a switch. Switch means allows the current to pass or stops the current to pass. So Pn junction can be used as a switch to open the circuit or close the circuit. Now, this is also like very clear here. If you look at this diagram above here, this diagram, yeah, this one. If you look at this diagram, in the forward biased, can you see here that we have current, and the current is the current. it can reach like 50 milliampere in this diagram. But if you look at, if I connect this in the opposite way means I connect it in the reverse bias connection, the current is very small and it is minimized. I can consider that the current will stop completely in this case. So if I look here at what's going on, I can control passing current in the circuit by having the Pn junction. It can work as a switch, okay? As you see, compare it between this, the current here and the current there. It's very obvious that in the forward current can pass and in the reverse direction current cannot pass. I have another application of the Pn junction other than to work as a switch. It can also work as rectifier. What we mean by a rectifier, we know that we have two types of currents. We have direct current and we have alternating current. The alternating current changes its direction and value. But one problem is, if I'd like to change the alternating current into direct current to be able to use it in cell phones or like electroplating or many other applications, I need to change the alternating current to direct current. Now, is it possible? Yes, it is. Using the Pn junction, I can rectify or change the direction of alternating current, change it into direct current by allowing current to pass in one direction and not the other. So when the alternating current reverses its direction, I will not take the negative part. I will take only the parts positive. So in this case, I will have a unidirectional current, which means that direct current. So the Pn junction can act to rectify the alternating current to change it into direct current. Okay, but there is a difference between last part. There is a difference between the Pn junction and ohmic resistance. Now, the Pn junction, I have two crystals, P and N, and ohmic resistance is made of coil. All right, so it's not made of two crystals, made of a coil. So Pn junction is made of two crystals, P and N. Charge carriers in ohmic resistance, always the convention one, electrons. Charge carriers in Pn junction, you have two charge carriers, positive holes or free electrons. So in ohmic resistance, I have only one type of charge carriers, which are electrons, free electrons. And in the Pn junction, I have two types of charge carriers, positive holes and free electrons. The electric current intensity in the Pn junction in one direction, it does not pass in the reverse direction. But in ohmic resistance does not pay attention to the direction of current. You can pass current from left to right or right to left. You can also reverse the direction without any change. Ohmic resistance is the same, but the Pn junction is not the same. In the forward is not like in the reverse bias. The last part is the effect of heat. Now, by increasing temperature, what happens to the ohmic resistance? It increases because many electrons will collide with each other, so that results in the reduce in current. So by increasing the temperature, the ohmic resistance increases. In the Pn junction, the exact opposite. By increasing the temperature, what happens is more electrons will break free from the bond, and this means that the conductivity will increase. So this is like a summary of the difference between the ohmic resistance and Pn junction. And by this, we come to the end of our lesson. If you have any question, don't forget to drop it and ask it. Thank you for listening. My name is Ahmad and I teach physics. And by this, we come to the end. See you next time. And
ليه ده؟
تيجي تتك عليها البتاع دي بتترعش.
بدل ليه بنفتح السهم كده ونقوم قايلين ايه؟
انا عملت ايه؟
انت عملت ايه؟ طيب بس انت قلت لي مش عارف.
ما هو مش عارف ليه، عشان الماوس بتلعب.
ماشي خلاص.